Let us have some examples. So the first example is a linear transformation. Suppose that W is defined by this linear combination and Z by this one. And we want to find the joint PDF of W and Z in terms of the joint PDF of X and Y. So the first step is to basically solve W is equal to AX plus BY and Z is equal to CX plus DY. So to do that, you could write this one in terms of A, B, C, D times, you can write these two equations in terms of X and Y equal to W, Z. So the first equation is A times X plus B times Y, and then the second equation is C times X, D times Y. So you could see that the solution XY is equal to inverse of this matrix, which is A, B, C, D inverse times W, Z. So we have one solution, one unique solution if this matrix is invertible, which is the case that the determinant of this matrix is non-zero. The second step is to determine the Jacobian. So if I calculate derivative of these with respect to X, then Y, then derivative of these with respect to X and Y, and then form these Jacobian and calculate determinant of this matrix, then we have to determine the determinant of A, B, C, D, and in this case this is equal to that. Now if this Jacobian is non-zero and then I have a unique solution, so if we solve these two equations, we can write it in a matrix form, and then you can get X, Y is equal to inverse of this matrix times W, Z. If you write the inversion in terms of that and then simplify, you get this. So you have this is only one solution. So there is a solution when AD minus BC is not zero. If AD minus BC is zero, then there is either no solution or infinite number of solutions. So when the determinant is non-zero, so you could see that this is equal to fxy at the solution. So x is equal to dw minus bz divided by ad minus bc, and replace y by this one, minus cw plus az, and then divide by ad minus bc, and then divide the whole thing by Jacobian, which is equal to this one, so ad minus bc. So this is the final expression. So the joint PDF of the output is expressed in terms of the joint PDF of the input and the coefficients of the linear transformation. So if the determinant is zero, so two things will happen. First of all, the Jacobian will become zero, so I cannot divide something by zero. The second thing, the second trouble is that the solution x is going to be something divided by 0, y something by divided 0, so there's no unique solution. So in this case, if this determinant is 0, it means that the second row is proportional to the first row. So obviously in this case it means that z and w are proportional to each other. That means that we don't have two random variables at the output. We have one random variable, and the second random variable is proportional to it. So this is called a degenerate case. Degenerate case means that the Jacobian is 0, or the solution is not unique. So so basically they are not equal, they represent the same random variable because they are proportional to each other. So these cases should be solved separately with a bit more attention.